So we are meeting after a long break, and so a quick recap for what we did in the last class before going on this break for the Diwali and Chhat Puja. Okay, so this was the thing that we started off in the last class. We were just started the discussion on electronic spectra of polyatomic molecules, and we started with this CC double bond, compared this with the C double bond O, that is carbonyl. So the two double bonds, CC double bond and CO double bonds, that were analyzed and discussed in terms of the electronic spectra कि कौन कौन से transitions हो सकते हैं, what is the possibility of some that transition to happen, probability, and the intensity of the transition. Both were discussed in the last class, and so we had this kind of thing, appearing the pi to pi star transitions. So that is very intense in these bonds, in double bonds. In addition to that, you can also have n to pi star transition, which is in case of unconjugated CC double bond, you will have it around 180 nanometer. As the conjugation increases, you will have this will shift to longer wavelength. That is, energy gap will be reduced. So that's what pi to pi transitions. Yeah. So conjugated. So something which was earlier in the ultraviolet range would now appear in visible region if there is extended conjugation over the chain. So that is something we can also link with our uh, this vision mechanism of vision that involves rhodopsin. So that is extremely conjugated structure, so double bond structure. And then we looked into the C double bond O. So here the additional thing that can happen is that there is a lone pair on oxygen. So N, this is the lone pair non-bonding orbital in, and this is the pi star. So N to pi star transition is also possible. This is a symmetry forbidden transition. As we know now what this forbidden transition, symmetry forbidden, what they mean, we have extensive discussion earlier in the previous classes. So this lone pair of electrons gives you this, but there is sometimes that what you know this transition will happen, but it will be very very weak. That is, when we say weak transition, means intensity will be less. So when you are seeing the so एक peak छोटा होगा, n to pi star वाला छोटा होगा. In terms of when you are plotting absorbance on the y-axis and wavelength on the x-axis, you will find that n to pi star transition will have small peak, appear as a small peak. It will have lower energy gap, so it will appear towards the longer wavelength side, and so it is appears around, so C, and isolated uh, case of C double bond O will have this thing C double bond O, 290 nanometer as the wavelength of this transition, or in terms of electron volts you can find it to be 4 electron. So that's it's a very weak transitions, that is intensity will be less. So these are the possibilities that we have in such polyatomic molecules. You can see in the picture all this sigma pi and pi star, sigma star. So all these transitions possibilities are shown over here. So most of the what you really observe is that these thick lines that you see, n to pi star is observable, very low intensity, it is observed. N to sigma star is also observed. Pi to pi star is also observed. These are thick lines that has been drawn over here. In alkanes, so this is with the double bonded things. These are the possibilities, but in alkanes there are no pi or pi star orbitals. In that case, you will have sigma to sigma star or N to sigma star transitions. That is possible, and these are much weaker absorption. Sigma to sigma star transitions would involve maximum energy. You can see sigma to sigma star transitions. This involves maximum energy and falls in the what we say short far UV side. Beyond the normally the instrument that we have उससे जो आपका है लैब में या कहीं किसी भी in any good lab the normal UV visible spectroscopic instrument will have 190 nanometers to 1100 nanometers, so it is much less than that, and so it is beyond this UV vis range which is normally available in the labs in any so sigma to sigma star transition practically speaking is not observed because the instrument capability is far beyond that the most common type of instrument that we use. Okay, but all other transitions pi to pi star n to pi star transition are very well observable in our labs or any other lab which has so this sigma to yeah so this is so if you think of sigma, if you want to know the range of sigma to sigma star, then it is around 122 nanometers in case of methane. You can also see that sigma to sigma star transition in CC bond, C double bond, sorry, C single bond C is almost slightly towards the longer wavelength side, 130 nanometers, and things change. So one more thing that we discussed in the last class, that was when you have a C single bond O, just as in methanol, CH3OH, and when O is replaced with S, so if you are moving down the group from oxygen to sulfur, what you can see N to sigma star transitions is happening. What is happening? So sorry, N to sigma star transition is moving to longer wavelength. पहले 183 nanometer पे था, now it is going to so when carbon is bonded to a chalcogen, oxygen and sulfur, the sulfur will the heavier metal, sorry, heavier element which is bonded will have longer wavelength of the N to sigma star transition. You can see this very clearly. Similarly, if you are comparing alkyl halides, you can also see this effect. Cl methyl chloride, methyl iodide, 173 nanometer, 258 nanometer. Okay, so N to sigma star transitions, they are usually weak, that we have already discussed. So intense. So to intensity, this if you want to quantify and talk about intensity, you need to know this absorption coefficient, the epsilon, which is also known as molar extinction coefficient, right? So the higher the value of this molar extinction coefficient, higher is the absorbance value for a given concentration of both two different analytes, same concentration of two analytes, different intensity. So that is because of this absorption coefficient that mathematically we can correlate with. So these are very small values, because if you want to something to be intense, we call it intense when it is like 16,000, 20,000 millions, 1 lakh times the value is like that, then that is, we call it intense. So that something different. Pi to pi star transitions are intense as compared to these sigma to sigma star and other things. N to sigma star, N to pi star is again weak. In here you can see as compared to in the same molecule you have pi to pi star transition and 2 pi star, so it is much weaker but appearing at a longer wavelength. Okay, so things can be this is how the absorption wavelength shifts when the atoms are substituted in a molecule. So as we have seen here, in going from halogen group chloride to iodide, or in case of chalcogens going from oxygen to sulfur, how the things will play out, that's now discussed through these things, through this slide. Similarly, you can see pi to pi star transitions. Some more examples are given which you can see for yourself. We have I'm not again going into this again. We have discussed earlier, and now I would like to move ahead. So practical, so that was a tabular representation of the pi to pi star transition and n to pi star, and this is the graphical one. The graph absorbance on y-axis, wavelength on the x-axis, n to pi star, a very small absorption signal that you can see, but the absorption signal will be high for pi to pi star transition. So that is the kind of thing you will get for a simplest molecule having C double bond O, that is formaldehyde. So this is coming at around, you can see 290. This is coming around something at 180. This is 220, 250, 220 something. Okay, so the same for the same C double bond O, the N to pi star can be under, if you are having extensive conjugation, as happens here in case of tetraphenylpentadienon. You can see that due to the extensive conjugation, the N to pi star transition, which was earlier in the UV range, now in the, it comes in the visible range में आ गया है. So this is a typical thing that has been observed. The pi to pi star transition also shifts to 343 nanometers. So to understand this conjugation, we can take example of ethylene to butadiene, construct molecular orbital diagram taking ethylene as the basic building block. So start with ethylene on both sides, just as you would draw any other molecule. You start with two atoms and make start with their take their orbitals and make the bonding anti-bonding combinations. So similarly we have these things, uh, bonding MO, this is bonding MO, and this is the anti-bonding MO. They combine in the so there is destructive interference occurring here, and we have anti-bonding MO, and the resultant molecule is your butadiene. We are talking about butadiene, so these are all butadiene molecular orbitals. So in this manner, what we observe that what we have earlier in case of ethylene, we were having only this transition which was possible, which was of higher energy, but now by arranging looking at this format of combinations, you can clearly see that now we have the lowest possible transition is this one, which is of lower energy. And so this is the reason why conjugation shifts the absorption to longer wavelength side. That is, if it was earlier in UV, absorbing in UV, now it can absorb in the visible range. If it was earlier observing the blue side, now it will absorb in the red side. So that is what we mean. We also call it redshift of the spectrum, absorption spectrum. Okay, so you can, if you have got the idea, then you can further extend it to hexatriene, ethylene, two ethylene combined to give butadiene, and three ethylene units will combine to give you hexatriene. So in that case, so you can clearly see that if you're looking at the lowest possible transition, lowest energy transition, that gradually becomes lower in terms of energy. Okay, so this is the effect of conjugation, and this is explained through taking examples of ethylene as the basic unit, and then you make molecular orbital diagram for butadiene, taking those two basic units, undergoing combination, constructive and destructive interferences of orbitals. Uh, so, an extreme example of this: ethylene, butadiene, then hexatriene, and then you extend it further, you will get carotene, which is naturally you can carotene. You see, in carrots you will get carotene, and this is an extended over 1 to, you can see, about 11 11 1 2 3 4 5 6 7 8 9 10 11. So 11 double bonds are there, you can clearly see that. And this is now, so gradual shift, you can see 160, starting from 165, 217 to 470 nanometer. So clearly in case of carotene it is in visible region, and that's why we see orange color of the carrots. Okay, so then what we so this is the thing that will be now new, uh, which was not discussed in the previous class. This is the effect of solvents. So the spectrum that you see on the screen is the spectrum of phenol dissolved in two different solvents. So phenol is the solute which is dissolved in isooctane as the solvent, or ethanol as the solvent. So this ethanol or isooctane is the solvent, and phenol is dissolved in two of these things. So what do you see here? You can clearly see ethanol is having OH group, CH2OH. So polar. This is, it can form hydrogen bonds. Hydrogen bonds, if the solute is also having such polar bonds, uh, possibility for hydrogen bonding is there. Okay, so in phenol, when it is dissolved in ethanol, it will have hydrogen bonding interaction with the solvent. When phenol is dissolved in isooctane, no such things will happen. It will be completely, phenol will be not having any further interaction, such extreme kind of interaction of that happens in hydrogen bonding. So you can clearly see the spectrum is affected. There's such a strong effect on this signal, absorption signal, that you can see here. So when you what you see here, the fine structure disappears when you have hydrogen bonding. That is a clear thing in case of ethanol. So phenol, when it is dissolved in ethanol, you cannot see any fine structure because of the, the bonds weakened. There are lots of sorry. All the fine structure disappear. Okay, and when there is no such hydrogen bonding interaction, the fine structure can be seen clearly. So you can see the fine structure only when you have non-polar. In case of non-polar solvent, you can see the fine structure is retained. In a okay, so what you see, why and how these things happen, we can try to understand few things about that. So this is just one effect that we were talking about. One of the effects is that the fine structure is lost for polar. So if the solute is having something like OH group solute, the solvent is also having certain groups which can form hydrogen bonds, which is polar and can form hydrogen. Then the fine structure will disappear. Okay. Other thing that we also see is that if you have is this molecule, if it is a conjugated carbonyl, if you have carbonyls, that will be significantly affected when you have a polar solvent, particularly in the alpha beta unsaturated condition. If you have conjugated dienes or aromatic hydrocarbons, the solvent effect is less seen. So why this happens? Because in case of carbonyl, there is lone pair on oxygen which can form hydrogen bonds. So in the previous semesters, I have told you about the hydrogen bonding. There's you need to have lone pairs. It is the lone pair that participates in the hydrogen bonding interaction. So if you have something of lone pairs of something suitable energy, then hydrogen bond interaction can happen with the solvent if that is polar and protic polar solvent. You can have hydrogen bonding interaction and the shift will happen accordingly. So you can see that maximum effect in the non-bonding orbital having the lone pair. This is the lone pair electron is here, and this is the most affected when the solvent is polar. So effect of solvent, so this is the case of non-polar and polar, polar and protic solvent means something which has which can donate proton or accept proton. Protic solvent is something that can donate proton, okay, that has ionizable H hydrogen atom. H plus ion can be given, okay. Protic solvent means H plus, ability to form H plus ions, okay. So that kind of solvent, then it is found that if the solvent is non-polar solvent to polar solvent, in that case, if you have and the solute is this carbonyl group, then the effect is this: the n to pi star is most affected. This n, the energy of non-bonding orbital is in presence of polar solvent, which protic polar solvent, the ns, you can see this is comes down, maximum decrease. So most affected in terms of energy, what you see here, this is, if I can show this with the dotted line. So this is the drop in energy of the non-bonding orbital, goes down in terms of energy due to the interaction with the protic polar solvent. Why? You can easily understand, because the lone pairs are attracted to the H plus ion of the solvent, and so it is, there's a this due to this interaction the energy will be lowered, okay. So you must have a clear idea of what we are talking about here. And then the next effect, you can see that pi star is also decreases, there is decrease in energy, but not to that extent. So maximum effect is of the non-bonding orbital is affected most. The pi star is the next which is affected, and the pi orbital the least affected. This orbital is least affected, and this orbital n is the most affected when you are changing the solvent from non-polar to polar protic solvent. And what we are discussing this in the context of alpha beta unsaturated carbonyl, alpha beta unsaturated carbonyl. Then if this is your solute, this is your solute, Solvent is something like say toluene, non-polar, absolutely non-polar, protic polar solvent, something like methanol. Then it will, this kind of thing can happen. Okay, so what you see here, just let me clear up the things, rub it off to make it. I've written too many things, so just a moment, let me clear it off. So what do you see here, that overall now the pi to pi star transition, so n orbital is most affected, it is going down in terms of energy. So the n to pi star gap, this one has been, uh, energy gap is lowered, del E n to pi n to pi star is now, this is less reduced, this is reduced now, reduced in terms of energy, so this will move to longer wavelength. So that is, so longer wavelength, uh, sorry, this one is increased, in fact, sorry, what I am talking about, this one is, क्योंकि n वाला जो है बहुत नीचे चला गया, पाई स्टार भी नीचे गया है, लेकिन वो उतना नीचे नहीं गया है. सो ओवरऑल इफेक्ट इज दैट n to pi star will move to shorter wavelength, high energy, so energy gap increased here, energy gap has been increased. And what you see here, pi star is dropping, pi is थोड़ा सा चेंज हुआ है, पाई स्टार में उससे ज़्यादा चेंज हुआ, सो ये गैप पाई टू पाई स्टार का ओवरऑल एनर्जी कम हो गया है. सो दिस इज मूविंग टू द लॉन्गर वेवलेंथ, n to pi star moves to the shorter wavelength. ओके, ठीक है ना. n वाला मोस्ट अफेक्टेड हुआ, पाई स्टार थोड़ा सा कम अफेक्टेड हुआ, सो ओवरऑल जो गैप है n to pi स्टार का वो बढ़ जाएगा. ठीक है, सो एनर्जी बढ़, गैप, एनर्जी गैप बढ़ गया, मतलब you are moving to the shorter wavelength side. If you are looking at the pi and pi star and then draw the arrow, you will find that the length of the arrow has reduced. That is, you have now moved to the longer wavelength side. So in a polar solvent, the non-bonding orbital containing the lone pair is most stabilized, and it is most stabilized in a polar solvent, and that's why you have, okay, and because of the hydrogen bonding, mainly due to the hydrogen bonding interaction, n orbitals are stabilized, and that's why we have maximum drop in energy for the n orbital, non-bonding orbitals, and because of that n to pi star moves to shorter wavelength. Okay, uh, so we can also talk about the electronic spectra in a, so that was electronic spectra of, so what we have discussed so far is the electronic spectra of polyatomic molecules. Particularly we have discussed the organic molecules, C double bond C and C double bond O in particular, what happens to them, what is the effect of solvent. So what we have, so what you have seen in these two slides tell you two different things. Two slides tell you two different things. The one is about uh, disappearance of this fine structure, vibrational fine structure in the electronic spectra, polar versus non-polar solvent. Second slide tells you about this, about what happened. So that was in case of any molecule that will happen. But if there is possibility of pi n to pi star transition and pi to pi, that is in happens in alpha beta unsaturated carbonyl, then you will see additional effects of the change in energy levels. Electronic energy levels will alter, that will, they will go undergo some n to pi star will move to the shorter wavelength, whereas that is they will increase in energy, and pi to pi star will have decrease in energy. Electronic spectra of DD transitions. So this is now polyatomic molecules in terms of metal ligand complex that we are talking about now. So now, so we are discussing, trying to discuss the electronic spectroscopy of both organic, inorganic systems, and you are already familiar with this. We have been discussing this since first semester. Electronic DD transitions, you know, T2G transition. So this is the simplest example of that. Titanium having one electron in d orbital. So this transition is very simple in an octahedral format. So H2O6. So, so yes. So you are now also familiar with Laporte selection rule, and we have already discussed the selection rules at length in the very beginning of this electronic spectroscopy. I told you there are two guiding things, guiding principles based on which we arrive at these selection rules. What are those? One thing is that development of transition dipole moment. So there must be a change in dipole moment for the interaction to happen. The light will interact with the molecule only when there will be some change in dipole moment. So there is electric field vector, oscillating electric field vector in the electromagnetic radiation. This oscillating electric field will interact with the dipole moment present in the molecule. So a transition dipole has to be created. If it doesn't happen, then no matter you are trying to provide the energy corresponding to the energy, sorry, you are trying to provide the electromagnetic radiation of energy corresponding to the gap, but no absorption occurs. So that is the case when you have G to G or U to U transition, that is G rate to G rate orbital or ungirate. So any molecule having center of symmetry will have this kind of behavior. We'll show you this kind of behavior. Yes, अभी class. Okay. Sorry. So I already told you about these things. So we have already discussed U to G, G to U in detail earlier. And this is the same thing, I think. Yeah. So first thing is that you must have a dipole, change in dipole moment. So here in electronic transition we talk of transition dipole moment, and that I told you that the transition dipole moment would be given by this integral. Sorry. Yeah. Sorry. What to say? Transition dipole. Transition dipole is usually dipole moment. This is given by an integral which is psi final mu the dipole moment operator into psi I. So the two wave function, two orbitals, two different wave functions. So imagine it in terms of one wave transforming itself into another wave format. Okay, उस तरह से विजुअलाइज करना है, समझे? कि सोचो कि एक वेव है, जैसे कि स्ट्रिंग को हमने दो जगह टाई कर दिया, एक हल्का सा प्लग किया तो एक सिंगल लूप वाला बनेगा, इसको थोड़ी सी एनर्जी और देंगे तो ये डबल लूप वाला बन जाएगा उसी फ्रेमवर्क में। उसी तरह से सोचना है, फाइनल साई एफ, इनिशियल साई आई। सो that kind of thing you have to imagine when you are talking about it. So, and what is the change in the, if there is change in the electron density profile, a dipole will develop. If there is no such change, then nothing happens, and that's why you have G to G transition, U to U transitions are not allowed because there is no dipole moment. Oh. So this mu is something that you easily know. Charge Q into R. This you already know. And we have in terms of electrons. So this is the electronic charge that we are talking about, Q, and it is the displacement that will happen. So that is with respect to R. So this is the electronic charge, and R is the displacement of that electron density, how it happens. So that is overall gives you this idea of transition dipole. So this integral must be a non-zero value, finite value. Okay, overall, and this will be finite, which I also already discussed in terms of odd even functions. So psi f or psi I must be overall multiplication, because this q into r itself is a odd function. So odd into odd will give you even function. So psi f and psi I must be a combination of odd and even function, and that is why we must have G to U or U to G transitions. If that is something, okay, ठीक है. So G rate symmetric with respect to center of ungirate. So this is already, you know, no, we don't have to be discussing. We have discussed it so many times. Yeah. Class. So we have this hmm, octahedral and square planar complexes. So this kind of thing will happen when you have octahedral in case of metal, if you have to, and in square planars which have center of symmetry. Tetrahedral complexes do not have this kind of thing, so this rule doesn't apply on them. And we are familiar for, so we are already familiar for atomic transition, whether it's atomic transitions in atoms or in molecules. This is very fundamental, that you must develop a transition dipole moment. Okay, so we have already discussed in case in last semester about transitions in hydrogen atom. So you know, S to P or P to D, what is allowed and what's not allowed, why it is forbidden. This you already know, right? You also know why this is forbidden. You should be able to explain these things, right? Why S to P is allowed but not P to D. Sorry, if P to D is allowed, D to F is allowed, but not P to F, S to D or S to S. So these are the things that we have already discussed, that why in case of hydrogen atom 1s to 2s transition will not happen, but 1s to 2p is possible. Okay, you have to conserve the angular momentum, total angular momentum, which involves the photon's angular momentum. And so that's how we arrived at that thing. So that second aspect of conservation. So first aspect was uh, which I also tell you in two things. So there are two selection rules. One is gross selection rules, and the other is specific selection rule. The first selection rule tells you whether transition dipole moment will develop or not. You must be able to, so the condition under which the transition dipole moment will develop and the interaction will happen. The second rule is always about the overall conservation of the angular momentum. So angular momentum of this uh, electron plus the photon system must be conserved. Photon has certain spin, and that it has angular momentum. The electron also has angular momentum. So this overall these things connect with those things. We have already discussed some of these aspects earlier, and the significance of this spin selection rule is that in very simple way is that del s must be there should not be any change in the spin of electron in these if we are discussing metal ligand complexes. So this is how we can simply put it. This is allowed because there is no, here it is spin inversion involved, and this is forbidden. Okay, so when we are looking at a D5 situation, you have to change this spin inversion. So this is a forbidden transitions. So because of this reason, MnS2O6 2 plus is Laporte forbidden, spin forbidden transition, and so it will be colorless Mn2 plus. But MnO4 permanganate, potassium permanganate, you have also used chromate ions in the lab. They are intensely colored, although they are D0 systems. So that is the charge transfer thing that can happen. So that we will discuss very soon about that. Why? So all charge transfer this absorption due to charge transfer from ligand to metal or metal to ligand are very very intense. You get very intense color of the system, and we will very soon we will discuss why it happens. So relaxation of Laporte selection rule we have previously discussed. If you have an octahedral molecule undergoing asymmetric stretching, asymmetric bending, so this the center of symmetry is lost for the moment, and at that point if a photon comes, absorption will happen, and U to U or G to G transition will we can happen. Tetrahedral complexes do not have such restrictions, so they do not have G2U designations. So usually in tetrahedral complexes you will have very intense color, very good strong highly intense absorption, light absorption happens in tetrahedral complexes. So usually this is what we find. We can summarize this for 3D complexes. If spin forbidden, Laporte forbidden transition, then you will have uh, very very low intensity, and that is discussed in terms of the molar extinction coefficient. What is this? This is the molar extinction coefficient or molar absorption coefficient. Okay, so this is an indicator of how strong your absorption is going to be. Or so spin allowed and Laporte forbidden. So Laporte, so you are discussing D to D transition, which is always Laporte forbidden, because yeah, they are all having same symmetry. All d orbitals are having g-rayed. They are all d orbitals are g-rayed, having center of symmetry. So they are Laporte forbidden, but in cases the if you are looking at T2G EG and EG is vacant, then the T2G is filled, then you can have spin allowed transition is possible. So that is the case of spin allowed transition. So there will be slightly more intensity in those samples. If you have spin allowed and Laporte allowed transition, that will be highly intense, and the maximum intensity you will find for symmetry allowed charge transfer bands, where ligand to metal, metal to ligand transitions, they are found to be very very intense. So this intensity is very very high, up to 10 to the power 6. The molar extinction coefficient is very high. So what do we see? Why do we see this kind of thing happening? Vibronic coupling. So it is, I also told you about this time scale of things. Vibration occurs about vibration happens about 10 to the power minus 13 seconds. whereas absorption will happen in the 10 to the power minus 18 to minus 15 range, femtos to attosecond range. And so this whenever this vibration whenever electronic transition happen, it is 1000 times, at least 1000 times faster than the vibration that is taking place. So typically for that moment the molecule is static when the photon is absorbed for an electronic transition happens. So in that case symmetry is gone, and you can have these are things that we have already discussed. Asymmetric, so a simple example of CO2 bending, these two are the modes where you have symmetry lost. Center of symmetry is lost, and then this transition can happen. Similarly, in case of, we can see this, there's another reason for why we see this forbidden transition, that is mixing of states. So uh, a pure D to D transition in isolated metal is not possible. That's what we understand. Okay, but when we have this kind of overlap of ligand orbitals with the metal orbitals, then they are not pure d orbitals. There's mixing of d and p orbitals, and so there's breakdown of the Laporte selection rule. So you can visualize this in this manner. You have metal at the center and six ligands occupying the edges, the corners of the octahedron, and this is the uh, orbital present on the metal, which is now having overlap with the ligands orbital. So this thing is now, this mixing of metal ligands with the ligands orbitals changes the basic nature of the orbital, and that is also part of the reason why this transition will have, forbidden transition can be sometimes seen with very weak intensity though. So symmetry is gone because of that reason also. Then third reason is the spin orbit coupling. So that also helps us in overcoming this blockade due to this uh, what we know, yeah, the Laporte rules. We can overcome this thing by, if there is a strong interaction of angular momentum with orbital angular momentum to give you a different total angular momentum of the system. So this happens in heavier transition metals. More often it is found in them, and this gives rise to transition which are otherwise spins forbidden. So that, to overcome spin selection rule, there is spin orbit coupling. To overcome the Laporte selection rule, you had two things: mixing of states, vibronic coupling. Okay, and so what we see here. So in general, a tetrahedron has no symmetry. So we do not give labels of E.g., G or U. We only write E or T2. That's one thing. So what you find here, when you have CH2O6 2 plus, this is an octahedral which is pale pink. You can see pale pink in color, but CO sulfur, which is tetrahedral, it is very dark in color. Same concentration, but the intensity of color. So there are two things that you can see. There is a absorption happening at a uh, sorry, longer wavelength. So, and then also there is also more absorption, greater absorption of the photons that come through, that is falling on the sample. So light absorption has increased, That is what we mean by increased intensity of color. Intense blue color is obtained for CaCl4, which is tetrahedral. This is tetrahedral complex, and this is octahedral. So typically cobalt that you can see here has pink solution, and the CaCl4 CuH2O6 is pink octahedral, and tetrahedral complex is more intense in color. Okay, so this is the transformation. So in practically, if you take the absorption spectrum of both these things, that is the octahedral complex, it will appear a very small absorption. It will show very absorption here, whereas if you take tetrahedral complex, the blue one, it will show a very intense band at a longer wavelength side. Okay, so this corresponds to this one, and this one is this. Okay, so because of the there's no symmetry, so Laporte's selection rule doesn't apply on it, and the transition happens freely. That is more easily. So you can generate the dipole moment very easily in such cases where there is no center of symmetry. Then there is charge transfer transitions. There are three types mainly that we can discuss here: ligand to metal, metal to ligand, LMCT, MLCT, and the third is intervalence transition. So typically what you will find, we have already discussed the example of Mn, Mn2s6 2 plus. It has very faint pink color is seen. It is spin forbidden, Laporte forbidden, and very faint pink color will be seen in this case. It's partly allowed by spin orbit coupling. That's why it appears like this. Otherwise you could not see any color. No absorption will happen if there is no spin orbit coupling. Then you can see cobalt complex, octahedral complex of cobalt, COH2O6. It is spin allowed but Laporte forbidden, slightly more intense color in solution phase, typical value of epsilon. We have just now discussed CaCl4 also, so it is tetrahedral. The energy is low, for the transition, energy required for the transition is low, and it is allowed transition, so it will have a high value of epsilon. Okay, epsilon, that is the absorption coefficient, is very high as compared to the other two cases. And the last one that we are seeing is the permagnet. You are familiar with this. It has a very high, such in general, such cases wherever you have this kind of, this is a D0 system, and the intense color that you see is due to the transfer of electron from oxygen to the MND band, sorry, MND orbitals. Okay, so that is the reason for this transition. So it gives at 528 nanometer, you can see deep purple color. So that is the reason for the deep purple color. So it is the oxygen lone pair, that one of that lone pair electron is going to the low lying orbital of Mn, the d orbital of Mn. So ligand to metal charge transfer you can understand through this cartoon. Metal, oxygen, you can see this. You have two electrons on oxygen, the lone pair, and the d orbital is vacant. So when the light falls on this in MnO4, so what you saw just now is that the electron jumps from oxygen to here. So this is oxygen going to this metal center. So this is Mn, this is oxygen, Mn orbital. So this is the charge transfer that happens. This is the example of LMCT, and this kind of transition is always happens, but in most of the cases it lies in the ultraviolet region. Okay, and that's why it is not too much important when we discuss in most of the cases. Some cases where this energy requirement is very low, it is observed in visible region, and there we see the vivid variety of colors appearing, potassium dichromate, uh, potassium permanganate. In those cases it will, you will see that it shifts to the visible region. So it is when you have a metal in a high oxidation state, this will happen. The this charge LMCT transition will shift to the visible region, and you will be able to see through naked eyes. Okay, so if the conditions for LMCT is that metal should be easily reduced, easy to reduce. Something will be, so that means it should have strong tendency to accept electrons. So a metal in high oxidation state will have a great urgency, a great need, hunger for this electrons to take up the tendency to take up electrons, and that will be ideal condition for LMCT to happen. If ligand is also in high easily oxidizable state, that is rich in electron, it has a lone pair of electron, then that is what we mean by, practically this is what we mean, that having a lone pair of electron is makes it easily oxidizable, the loss of electron. So so this kind of thing will happen, and if it happens, then it will intense transitions will be seen. So uh, So example of this you can find here: TiO2, vanad VO4 3 minus, chromate CrO4. All these are example of D0 system. D0. So DD transition to हो ही नहीं सकता. So the transition that what happens here is the charge transfer. Oxygen lone pair electron is so as the charge, so Ti4 plus V5 plus, so oxidation state is gradually increasing on moving from left to right. So higher oxidation state, the metal will easily accept the electron. So greater is the tendency to get reduced, greater is, and therefore you will see gradually the color, the energy requirement is reduced, and it will appear in the visible region. So you can see gradually. So 4 plus to 7 plus, oxidation state changes, and so is the reducibility, and the color shifts to longer wavelength side. Okay, so it appears in the far UV side, TiO2. You can see no color. It is appears white, but vanadate VO4 3 minus, that still appears white. Chromate appears yellow, and it appears, so gradually you can see it is shifting to longer wavelength, lower energy or longer wavelength, longer wavelength side. So that is high oxidation state is a very good scenario for ligand to metal charge transfer to happen, and the requirement for that energy requirement is reduced. It happens in the so starting from the UV side, you can see that the same LMCT transition now happens in case of MnO4 in the visible region. Okay, so so metal should be easily oxidizable. It must have low-lying empty orbitals to accept the electrons, and So this is the case for the metal to ligand charge transfer to happen. Easily oxidizable मतलब इलेक्ट्रॉन लूज करना है, easy to lose electrons. It must have electrons, enough electrons. So a metal in low oxidation state, so metal in low oxidation state will be is the kind of situation where electrons will be lost easily. Okay, metals, if it is rich in electron, if it is low in, so it is, and then the ligand must have low lying empty orbitals. So such kind of situation is encountered in bipyridine, uh, this kind of ligand. Okay, so you can find this happening in metal 2 plus, Fe2 plus, ruthenium, osmium 2 plus complexes with bipyridyl. So so there is excitation of electron from the metal T2g6 orbitals into the empty, so it is filled T2g6, completely filled T2g6 set of orbitals. Empty ligand orbitals is there on the that is the pi star orbital, and that, so it is excitation from this orbital to pi star orbital which is giving you the color. So this is MLCT, and this principle of can be utilized for capture harvesting the solar energy. Okay, so why are these charge transfer spectra so intense? What is the reason? इसमें खास बात क्या है? Dipole moment क्या होता है? So what we have already understood from our previous discussion, that intensities depend on the square of the dipole moment. Okay, intensity of charge transfer time is proportional to the square of the dipole. So greater is the value of dipole moment, greater will be the intensity. So now dipole moment क्या होता है? Q into R. R is the displacement, R is the distance or displacement of the charge that is happening. So it is the electronic charge, how far it is displaced. So if R is large, if R is large, dipole moment will be high. Dipole moment is also large, it will have higher value. And so now in this case what happens, the electron, see, in a normal metal, if the transition happens from d orbital to d orbital within a metal, the electron moves a small distance. But when this is kind of charge transfer happens from one atom to another atom, ऑक्सीजन से मेटल पे जा रहा है, तो डिस्टेंस ज़्यादा ट्रेवल करना पड़ेगा. इट विल बी अ लॉन्ग डिस्टेंस as compared to that initial first case. Within an atom जो ट्रांजिशन हो रहा है उसमें ध्यान दे रहा है? आर यू लिसनिंग व्हाट आई एम सेइंग? ध्यान दीजिएगा, ये बहुत इंपॉर्टेंट पॉइंट है. एक ही मेटल में इलेक्ट्रॉन एक ऑर्बिटल से दूसरे ऑर्बिटल में जा रहा है, ठीक है, एक ही एटम में. और ये दूसरा केस है जो इलेक्ट्रॉन पहले ऑक्सीजन पे था वो अब मेटल के अंदर जा रहा है. सो इट इज अ ट्रेवलिंग अ लॉन्गर डिस्टेंस. Okay, so the value, if you are calculating dipole moment, the value is increased, and greater is the dipole moment, greater will be the better will be the interaction with the electric field of in the in this light, and so you will have greater absorption of light. So that's why they are so intense. ठीक है, लेकिन अब इसका मतलब ये भी मत समझो कि जितना दूर करते जाएंगे उतना अच्छा होगा. नो, we have also seen that the transition dipole moment depends on the overlap of the two wave functions. So if you increase the distance to very large one, this is the mu that we were trying to write, and with transition dipole we show by writing this psi f mu cap and psi I. So this was the dipole, transition dipole moment that we can write integral. So this thing, so एक तो हो गया dipole moment का, लेकिन अगर हम distance बहुत ज़्यादा कर देंगे, if we increase the distance too much, then the overlap between the wave function psi f and psi I will be less, and that will also reduce the overall value of transition dipole moment. So it is a kind of situation where you must have optimum distance between the acceptor and the donor. Okay, then you have the best case scenario that you have a high value of mu, the dipole moment operator, and also a good overlap between the wave functions, the two wave functions, one orbital, another orbital, one orbital on the oxygen, so उसका wave function, और फिर जो d orbital का wave function. So this is yeah, so this is the way to understand why charge transfer spectra are so intense. Ten minutes तो बाद में. Okay, so कितना टाइम हो गया? ठीक है, हाँ, 5 minutes. Just I'll try to finish this thing. So the reason is that you have a large distance of migration is to be covered. A large distance, relatively a larger distance is to be covered when the electron moves from ligand to metal, okay, or vice versa, metal to ligand. ठीक है, and therefore you have large dipole value of the dipole moment and high intensity of absorption. ठीक है, but as I told you, if you're looking at the dipole moment, transition dipole integral, it also involves the overlap of this wave function, initial and final wave function. If the overlap is 0, then again the value will go to 0. So it has to be in a suitable space, same region of space. So this the two, the donor and acceptor, must be close enough. Okay, it's not that you go on increasing the distance, the dipole moment will go on, transition dipole will increase gradually. So this happens at an optimum distance. So larger distance favors high intensity on account of high mu value of the mu, the dipole moment operator, the dipole moment that we have, simple calculation. But if we go on increasing the distance, there will be less and less overlap of the initial and final wave functions at very large separations, and that will favor low intensity. So it is a compromise of the two, which we see in these cases, that it is bound, there is already a sigma bond which is bringing them close enough to each other, and then this kind of transition happens from a non-bonding orbital to the vacant d orbital of metal, or vice versa. Then a third type of transition that we were talking about, this is also comes into charge transfer category, that is intervalence transition. So the previous one was ligand to metal, metal to ligand, and in this case it is the example that we have for Prussian blue, where the formula is like this: Fe, you have Fe3, you have Fe2 plus ions, which is surrounded by Cn in octahedral framework like this, and this is the structure we have. So the charge transfer happens from electron is transferred from this to Fe2 plus to Fe3 plus. So momentarily, so both are metal, both are iron atoms, one having 2 plus charge, one having 3 plus charge. So Fe2 loses one electron momentarily, which is transferred to Fe3 plus, And so this is the intervalence transfer. This is also very namaskar system class khatam karte hain. Okay, so this we see here uniform Prussian blue. The name comes from Prussian army. बचे आया नहीं तो ऑनलाइन ही ले लिए. ऑनलाइन में भी सब नहीं आ रहे हैं, सब बड़ी मस्ती कर रहे हैं. ठीक है सर. हाँ, एक मिनट बस. सो ठीक है. सो दिस ब्रिंग्स अस टू द एंड ऑफ दिस electronic, not the electronic spectroscopy. One part of the half of the electronic spectroscopy has is coming to a finish line that we can see. You can just try to see the structure, how it is a very complex structure. The Prussian blue has, which has each Fe surrounded by Cn4. Then you also have Fe, so Fe2 plus and Fe. Okay. So if you are looking from the molecular orbital picture, then the transitions that you can describe as LMCT is the transition that happens from L sigma. So this is the molecular orbital having greater contribution from ligand to metal, and this is the T2G EG orbitals, so having more contribution from the metal, closer to the metal, so metal character. So if a transition happens from this orbital to either EG or T2G, so this is called LMCT, red one, LMCT transitions. Okay, so similar thing over here. This is having greater contribution from ligand. So this, so any transfer of electron that happens from this to this orbital, from we call it ligand to metal transitions. MLCT is something, is a transition that involves excitation of electrons either from this T2G level or the EG level, okay, to the pi star orbital of ligand that is contributing to this molecular orbital. Okay, so this is again shown here in the same framework, similar, same thing. And these are the examples of different structures that happens. Okay, so different, so the same thing pictured in a very different way. You can say the ligand sigma orbital, ligand sigma pi orbital, these are metal orbital, these are green ones that you can see. So any transition that happens from ligand pi orbital to the EG or T2G orbitals of the metals, that is LMCT. This is LMCT. Anything that transition that involves transition of electron from this to this is MLCT. Okay, so try to solve the problems, arrange the given in the order of increasing intensity. You can easily do this now. Fe4, Fe6, Prussian blue. This is, so which one will be having most intense and which one will be having least intense transition? You can now easily solve this. So that brings us to the end of absorption spectroscopy. Remember I told you the electronic spectroscopy has two parts. One is the absorption of light, and in the next class we will start the what happens to this electron which are already in excited state. They will try to relax, वो वापस आना चाहेंगे, they will try to come back to the ground state. So that is what we call relaxation, and that is observed as in terms of emission of light can happen in that case when the molecule tries to come back from excited electronic state to a ground state. That is, the electron will come back from the upper electronic energy levels to lower ones. There is chances of equivalent amount of energy will be lost in form of radiations, that will be emission of light. So fluorescence, that we will see in the next class, that will happen. We'll discuss this emission of light, and this aspect will be discussed in next 3-4 classes. The fluorescence, the luminescence, that we properties that we will be discussing in this class. Thank you so much.